Okay, so uh, in this week we are going to see number 6 of last year. So we have already seen the solutions for first 5 assignments. Uh, I am re-recording this lecture because there was some issue in the recording of live interaction session. So yes, let's start. So the first question is, which of the following are unital subrings of Q? Uh, Q is the group of ring of all rational numbers. So, and a subring is a subset of a ring which itself satisfies all set properties of a ring, and thus it's a ring in itself. And by unital, it means a subring that contains the unity, the multiplicative identity of the ring. So unit of Q, as we all know, is identity, that is 1. And so let's name these sets as, so let S1 be the set of all rational numbers with odd denominators, and S2 be the set of all rational numbers with even denominators, and the S3 be the set of all rational numbers with odd numerators. So these are three options. So I have just named them as S1, S2, S3, nothing much. So now, by just looking at these sets, first of all, we can cancel out some options, the ones which do not contain the unit. Whether the other is, whether they are rings or not, it's a second question. But we can directly see that which subsets contains the unit, that is the identity. So you can easily see that S2, that is the set of all rational numbers with even denominators, it does not contains identity. Why? Because you can see that you cannot write one as the in the form of p by q, where q is a even number, right? We of course want p and q to be co-prime. So one cannot be written in that manner. So that's why identity is not there inside S2. So S2 definitely is not the candidate for our unital subring of Q. And you can easily see that S1 and S3, they contains 1, because S1 is the set of all rational numbers with odd denominators. So 1 is uh, what is the presentation of 1 as a rational number? It is just 1 by 1, right? So if you want to write 1 as in the form of p by q, so it is just 1 upon 1. So it has odd denominator as well as odd numerator. So 1 is present in both S1 and S3. It is a rational number with odd denominator, and it is also a rational number with odd numerator. So now we have to check whether S1 and S3 are subrings. They are unital subset of Q. They contains the multiplicative identity, but we need to check whether they are subrings or not. So for S3, you can see that it is not even closed under the addition. If you as we have already seen that 1 is inside S3. So if you take any if you add 1 any number of time, then it's not there inside S3. Even number of times, then it's not going to be inside S3. For example, if you add 1 twice, 1 plus 1 is 2, then you have 2 is a rational number with even numerator. But in S3, you have all rational numbers with odd numerators. So 2 is not there inside your S3. So S3 is not a unital subring of Q. And the reason is because it's not closed under addition. Because uh, S3 is not closed under addition, right? So if it is not closed under addition, it's not even an group under your additive operation. So it's it's definitely it's not a, what ring. If it's not an additive group, then it's not going to be a ring. Now for S1, we have already seen that S2 and S3 are not the correct options, but we have to prove that S1 is the correct option. We have already proved that identity is there inside S1. So it's a unital subset, but we need to check that whether it's a unital subring or not. So for that, we pick two uh, members of S1, A by B and C by D. So again, S1 is a set of rational numbers with odd denominators. So if A by B and C by D belongs to S1, then that means that B and D are odd integers. Okay. Also, how we are subtracting two rational numbers. So A by B minus C by D is just AD minus BC upon BD, and it is again an element of S1, because if B is an odd integer and D is an odd integer, then BD is also an odd integer. Okay, so that's a trivial fact. So I'm just restating it. Since B and D are odd integers, therefore BD is also an odd integer. Okay, so that's it. Now, so it's a subset of Q such that the difference of two elements is again inside S1. So it is an additive subgroup of Q. Now it is also abelian, because abelian is a property inherited by Q. So it's also abelian, and uh, we need to now check the properties regarding the multiplication operation. So A by B dot C by D, it's AC upon BD. Now it is inside S1 again, due to the same reason. Here the same reason will uh, come again. So as B and D are odd integers, so BD is also an odd integer. So if AB and CD belongs to your S1, then AC upon BD will again be inside your S1. So, and associativity is already inherited by the Q. So thus S1 is a unital subring, okay, of Q. Yeah. So let's move on to the question number two. So it says let R be the set of infinite subsequences of integers a1, a2, so on, and where all but finitely many of ai's are zero. What does this means? That it is a sequence of integers in which everything is zero except for finitely many except for finitely many ai's. Then it says R under component wise addition and component wise multiplication is it a group or a group but not a ring, or is it a unital ring or a non-unital ring? So we will see, there may be more than one options correct. So we will check one by one whether it's a group ring or unital ring or non-unital. We will check one by one. So first of all, let's understand the operation. So if a1, a2, so on, this and b1, b2, and dot dot dot, these are two elements of R, then the difference of two elements a1, a2, and this minus b1, b2, so on to this is a1 minus b1, comma a2 minus b2, and so on. So yeah, I am directly writing minus without even giving the existence of inverse. That's a problem. So let's first deal with the plus one. So this is the addition operation. This is defined like this. Okay. Now AIs are integers and BIs are also integers. So AI plus BI is also an integer. So and so it's a sequence of integers. But we need to check more. We need to check that all except finitely many indices, each AI BI is zero. Okay, so that's why I am writing here if finitely many AIs and BJs are non-zero, then AK minus AK plus BK I should write AK uh, plus BK is non-zero for finitely many case. Why? Because at the indices where AI, AK and BK both are zero, then their sum is again going to be zero. So it's only about those indices where either AK is non-zero or BK is non-zero. Okay, so only for those indices we have the possibility of having AK plus BK to be non-zero. Except those indices, everywhere else we will get AK plus BK to be zero. And those possibilities are finitely many. That's why AK and BK is non-zero for finitely many cases only. And thus this addition, after addition, your element A1 plus B1 comma A2 plus B2 is it is inside your R again. Okay, because each of these and this entry is an integer and only finitely many uh, components survives. All others are zero. Okay, just a second. Now the inverse also we can see inverse of A1 comma A2 dot dot dot. Its inverse is just minus of A1 minus of A2 dot dot dot. It is again inside R. Okay. I need some space. Yes, I can take some space from here. Yeah. Before talking about the inverse, we should uh, say something about the identity. So identity is, you can see, let me write it in some other color. This 0, 0, comma 0. Oh, it's this thing. This is inside R and it is your additive identity. Okay, so you have closure, you have additive identity, you have inverse, and associativity also follows trivially, that you can check of your own. That it's a group, and apart from associativity, you also have the commutativity. So both of these are trivial to check. So I am leaving it for you. Commutativity, it will also follows. Okay, now A1, A2, A1. Let's now move on to the mm, multiplicative operations. So if you multiply two elements, then their product is a1 b1 comma a2 b2 and so on. Now ak bk is non-zero if and only if your ak is non-zero and bk is non-zero. As your ak is non-zero for finitely many places and bk is non-zero for finitely many places, or so ak bk is non-zero only for finitely many places. And my product of two integers is an integer. That's why this sequence is again inside your R, so it is closed. And then associativity here, Associativity also follows trivially. Okay, so I'm just writing multiplicative multiplicative, so associativity, it follows trivially. Okay, thus R is a ring. Okay, now the question is whether whether the multiplicative identity is there inside R or not. So let C1, C2, so on to be an element of R, which claims to be a unit or multiplicative identity. Instead of unit, I should write multiplicative identity. Mm, the multiplicative identity, the multiplicative identity. If there exists such an element, then what happens? Then you should have a1 a2 multiplied with this c1 c2 up to be again a1 a2 a2, right? And this should follow for all a1 a2 dot 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 inside R. But what if this is true? Then you have a1 c1 comma a2 c2 equal to a1 a2 a2 again, and this will implies ai ci equal to ai for all I, and that will implies that your ci is equal to 1 for all I, because this is a product of two integers. So now you are inside your the ring of integers, so there ai will cancel out to this ai, and you have just ci's. So ci has to be equal to multiplicative identity of integer, that is 1. So this will imply that your tuple c1 c2 so on to this is 1 1 comma 1 comma 1, but that is not inside your R, because uh, here you have everything to be non-zero. Okay, this is not inside your R, because here each coordinate is non-zero. But according to the definition of R, you must have only finitely many coordinates to be non-zero, so it's not an element of R. Thus, multiplicative identity is not there inside your R. So R is a non-unital array. Okay. Now let's move to the example number 3. It says in the above example, if we consider the map phi from R to R cross R given by phi of A1, A2, so on to A3, A3, so on, equal to a1 comma a3, so on comma a5, and so on to it is just putting all uh, ai's where I is an odd index in the first coordinate, and then all even index coordinate in the second uh, coordinate of this r cross r tuple. So then the map phi is, first of all, is it a ring of homomorphism? If it is a ring of homomorphism, whether it's a surjective one or an injective one, we need to check that. So you can easily see the property of ring homomorphism is satisfied very trivially. Phi of A plus B is going to be phi of A plus phi of B. That I'm not going to check. And phi of AB is phi of A dot phi of B. Because if you add them, then you can again distribute them at the level of R cross R. Okay, and similarly, if you multiply them, then you are free to distribute them at the level of this R cross R tuple. So you can check that these two properties will be satisfied trivially. Now for the subjective part, let's say some C1, C2, so on this tuple, and D1, D2, these are some tuples in R, and corresponding to them, we have this C1, comma D1, comma C2, comma D2, so on inside R, such that if you apply phi to this tuple, then you will get its image as C1, comma C2, C3, so on, and D1, comma D2, D3. Because what phi does, phi separates the odd coordinates C1 C2, C3 here with the even coordinates that are just D1, D2, and D3. So corresponding to any element of R cross R, because we are picking C1, C2, Cn, C1, C2, so on, and D1, D2, dot 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 as arbitrary elements of R. So they are are coming from arbitrary tuples of R cross R. So corresponding to that element, we always have an element of R such that when phi is applied over this element, you get C1, C2, C3, and D1, D2, D3, so on. Thus, phi is surjective. So checking whether phi is surjective is easy, and injective is even easier. So if phi of A1 comma A2 so on to this is same as phi of B1 B2 so on, then what will you get? Then phi of what is the value of phi of A1 A2 so on? Again separate the odd coordinates A1 A3 A5 so on, and A2 A4 this is an element of R cross R, and then phi of B1 B2 B1 B2 B3 so on is phi of B1 B3 B5, and thus so on, and B2 B4 dot dot dot. So now compare these two tuples at the level of R cross R. So the first coordinate, that is A1 A3, will be equal to the first coordinate here B1 B3, and the second coordinate A1 A2 will be same as B1 B2 B4, and so on. Now you can compare their individual coordinates, and you will get AI equal to BI for all I, and that will implies that your A is equal to B. A was your A1, A2, so on, and B1, B2, B3, and so on. So your if each coordinate AI is same as BI, then your A has to be B. Thus, phi is injective. Okay, so this homomorphism is an injective and a surjective homomorphism, surjective ring homomorphism. Now let's move to the next question. This question says that which of the following are integral domains? So first is Z modulo 5Z, second is Z modulo 7Z, third one is Z modulo 25Z, and fourth is Z modulo 9Z. So there is a result already. You all might have seen that. Just a minute. That Z modulo NZ is a integral domain if and only if your n is a prime number. So if you use that result, then you can directly say that Z modulo 5Z and Z modulo 7Z are integral domains, but Z modulo 25Z and Z modulo 9Z are not integral domains. But we will try to prove it without using that result, and in the course of that, we will also prove that result, which is an very easy, which has a very easy proof. So let's first see why Z modulo 25Z is not an integral domain. Okay. So an integral domain is a ring with all integral domains has this property, right? If AB is inside A comma B, these are two elements of your ring, say R, such that AB is zero, then either A has to be zero or B has to be zero, right? So if we could find two elements in Z modulo 25Z such that their product is zero and none of the element is zero, then we can say that Z modulo 25Z is not a integral domain. So what is the zero? What is zero in Z modulo 25Z? It is just mm, the zero coset, that is 0 plus 25Z. Okay, or just you can say 25Z. So and we have this non-zero element 5 plus 25 of Z inside your Z modulo uh, 25 of Z. Let me just write it more clearly. Sorry, it is 25 of Z. Okay. So it is some non-zero element inside your mm, Z modulo 25 of Z, such that if you multiply the element with itself, then you will get 25 plus 25 of Z, that is your 25Z again, which is the zero of your Z modulo 25Z. So you get two elements A and B, which is in this case same, are same elements, such that If you take the product of them, then you are getting the 0 of z modulo 25z. Thus, your z modulo 25z is not an integral domain. So parallelly, you can see for z modulo 9z, you have 3 plus 9z, a non-zero element inside your z modulo 25z, such that if you take the product of it with itself, then you will get 9z again, which is a 0 of which is 0 of your ring z modulo 29 z modulo 9z. Thus, it's not going to be an integral domain. Okay, so what special thing you have when you are working with primes, that we are going to see, and we will in general prove that z modulo pz is an integral domain. Okay, so for z modulo pz, where p is a prime, if you have a plus pz and b plus pz, two element of z modulo pz, such that their product a plus pz and b plus pz is pz again. Pz is a zero of it is a it is a zero of z modulo pz. So if you have their product as the zero of z modulo pz, then what does this means? Their product is thus just ab plus pz. So if ab plus pz is equal to pz, what does this mean? It means that ab is inside your pz, and that implies that p divides ab. And being a prime, if p divides ab, then it means that either p divides a or p divides b. But if p divides a, it means that or I should write it more. Uh, I can add one more step here. So if P divides A, that implies that A is equal to some P alpha, and which implies A belongs to PZ. And if A belongs to PZ, this means A plus PZ is equal to PZ. Same thing here. P divides B implies A equal to P beta, uh, which implies A belongs to PZ, and that will implies that A plus PZ is equal to PZ. This is for some beta belongs to the integer. Okay, I think that is obvious. I can just omit it. Okay, yeah. So now one can check that z plus pz is an integral domain if p is prime. That is one non-trivial thing. Except it, you can check the properties of addition and multiplication of your own. And z modulo nz is a ring, uh, mm, commutative ring. Okay, so you can check all these properties, and you can come to the conclusion that z modulo pz is an integral domain if p is a prime. What happens when p is a composite number? That if say p is a composite number, and some mm, say a and b are two numbers which divides p, okay, and a and b are not identity, then you can write p as a dot b, which means that you can write the coset pz, uh, sorry, as a plus pz dot b plus pz if p is not a prime, and thus a and b are non-zero, are uh, not the divisors of uh, p is not able to divide those numbers. So you will get that a plus pz dot b plus pz is equal to pz again, such that none of your a plus pz and b plus pz is zero. So that's sort of idea I'm giving. So you can prove that for each composite number, say p, don't use the notation p for each composite number m, z modulo nz is not a integral domain. Thus, it is an if and only if statement that z modulo nz is a integral domain if and only if your n is a prime p. Sorry, n is a prime. Okay. Now moving on to the next question. Next question is, which of the following are integral domains? Okay. So first one is zx. modulo the ideal generated by x square plus 9. Second is zx modulo the ideal generated by x square minus 9. Third is zx modulo the ideal generated by x cube plus x square plus x plus 1. And fourth one is zx modulo the ideal generated by x cube plus x square minus x plus 1. Now, let's first understand the structure of this uh, ring, and then we will move ahead. So zx modulo fx, that is generated by fx. We are working with this. If gx and hx are inside zx, such that gx plus fx dot hx plus fx is is 0, that is ideal generated by fx. What does this mean? It means that gx dot hx plus fx is equal to the ideal fx generated by fx again, and that will imply that gx dot hx is inside your ideal generated by fx. Okay, so that's the basic thing. Now let's see some definition. So we say that an ideal I is a prime ideal if for all AB inside R, AB belongs to I, imply either A belongs to I or B belongs to I. Okay, so and then you have a statement that one I any ideal of zx is prime if and only if zx modulo I is an integral domain, because zx is a special ring, it satisfies certain properties. I'm not listing out those properties. It's a task for you guys that what special properties this zx has, such that zx being prime, it implies uh, it's an if and only statement that if any ideal is a prime, uh, if and only if the corresponding uh, modulo ring is an integral domain. That means that I is a prime ideal if and only if zx modulo I is an integral domain. So if you want to check that zx modulo I is an integral domain, it is enough to check that whether the ideal is prime ideal or not. Okay. Yes, and a prime ideal is generated by a prime element, and here all irreducible elements are prime. So if it is a prime ideal, then it has to be generated by some irreducible element. And you can see that x square plus 9 is an irreducible element in zx because it is irreducible in your rx also, right? It has no real roots. It has complex roots. Definitely, it is going to be irreducible inside the ring zx. Okay, so x square plus 9 is a irreducible element or a prime element in this case, and thus x square, the ideal generated by x square plus 9 is a prime ideal, and which by the above statement means that zx modulo x square plus 9 is is an integral domain. Okay, so it uses some properties of commutative algebra that I leave to you guys to go and check these properties once, and it's not difficult to prove them. They are very easy, and you might have seen them in uh, some in first course of competitive algebra. Otherwise, you can if you have not done that course for the moment, you can just believe that these are this is true, and then when you get the chance to read that course, you can try and prove them of your own. Okay, so it's a prime ideal, that's why this modulo is a integral domain. Now, what about this zx modulo x square minus 9? See, it is a reducible element because x square minus 9 uh, has integer roots at minus 3 and plus 3. So you can see that x plus 3 plus x square minus 9 is and when you multiply it with x minus 3 plus x square minus 9, so these are two elements of this. They certainly belongs to this, uh, right? X square zx modulo x square minus 9, they certainly are elements of this ring. And you can see when you take the product of them, it's going to be x square minus 9 plus the ideal generated by x square minus 9, and it's again the ideal generated by x square minus 9, and it's a zero of it is the zero of your ideal your ring zx modulo x square minus 9. So these are two non-zero elements such that their product is a zero element in this ring. So thus zx modulo x square minus 9 is not an integral domain. Okay. Now, this polynomial you might have seen many number of times. It has integer roots, and the roots are also mm, easy. You can just using your mm, hit and trial method, you can find an integer root. Okay, finding an integer root is enough. You know to check that whether the all three roots are real or non-real or complex, whatever it is. But if you find an integer root, that is enough to prove that the mod integer this ring is not an integral domain. Okay, so you can see if you put x equal to minus 1, okay, then it is minus 1 plus 1 minus 1 and plus 1. So minus 1 is the root of this polynomial. Thus x plus 1 is a factor of x cube plus x square plus x plus 1, right? So this polynomial is an irreducible is a reducible polynomial. So if it is a reducible polynomial, it implies that it is this is not an integral domain. Okay, if I have some space, then I can elaborate. Yes, so let's elaborate it a bit. How can we see it's not an integral domain? So x cube plus x square plus x plus 1 is x plus 1 times, take x mm, plus 1 x square plus 1, right? X cube plus x square plus x plus 1. Yeah. So what does this mean? This means that when you take x plus 1 product of these two elements, it's an element of zx modulo x cube, ideal generated by x cube plus x square plus x plus 1. Take the product of this element with this element, right? Then you are supposed to get the ideal generated by this element again, which is a zero of which is a 0 of zx modulo x cube plus x square plus x plus 1, right? As it is a 0, it is a 0. We can say uh, you have two non-zero elements inside this ring whose product is 0. Thus, this is not going to be an integral domain. Okay. Yeah. Now for the next, uh, it's up to you guys to see that this polynomial x cube plus x square minus x plus 1 is not an integral domain. Sorry, is an integral domain because it has this polynomial has no root in z. Okay, as it has no root in z, it is irreducible inside z, uh, irreducible inside zx. Here being irreducible also means being prime. Thus the ideal generated by this polynomial is a prime ideal. So zx modulo this prime ideal is an integral domain. Okay. So only thing you need to check that this polynomial has no integer roots. That I am leaving up to you to see that why it does not have an integral root. Now let's move to the next question. It says for an integral domain R and an integer n greater than 1, let DNR be the ring of n cross n diagonal matrices with entries in R. You need to check whether the statement is true or false. Statement is D and R is an integral domain. Okay, so R is any integral domain, and uh, n can also be vary. So whether this is true in general. So this is not going to be true in general. You can first example, you can see if you take R to be the ring of uh, real numbers, then 0 comma 0 0 0 1, it's an diagonal matrix. uh, so it's an element of D and R. And 1000, it's also a diagonal matrix, so it is an element of DNR again. And if you take the product of these two, then it's going to be a zero matrix. So you have two non-zero elements of DNR such that their product is a zero matrix. So DNR is not an integral domain, so the statement is not true in general. So what about a general proof for it? Can we prove it generally, that whether for every integral domain and for any n we can find such examples or not? So that we will see. Just write it more clearly. This statement in general, if R is a non-zero, definitely non-zero we are taking is an integral domain, then for any non-zero element of R, if we have these matrices A 0 0 0 0 0, everything is 0 except your first entry, and here everything is 0 except the entry mm, 2 comma 2. We are taking n to be greater than 1. Okay, so at least n has to be greater than equal to 2. So both these matrices are there inside your uh, DNR. So these two are inside your DNR. Okay, it is also inside your, this also belongs to DNR. Don't get confused. It's not a real ring of real number. It's and now we are working with any arbitrary ring. Now for that, these matrices also, if you take the product, then it's again going to be a zero matrix. So for any ring R, for any integral domain R, you have those two matrices such that the product is zero, but none of them is a zero matrix. So DNR is never an integral domain, even if you are given that R is a integral domain. Okay. So what are the so the next question is, what are the quotients and remainders respectively in ZX when Px, which is x cube x4 plus 2x cube plus 3x square plus 3x plus 1, this is divided by qx equal to x square plus 1. Okay. Mm, this is divided, so you have the polynomial to be this and the dividend to be x square plus 1. If you divide it with this, then uh, what will you get? Okay, so yeah, it's just a division as you do in the division of polynomials. The only thing here, you the interesting thing would have been if you are not getting some integer coefficients, but here you are getting you will always get integer coefficients, so there is nothing new here. So you just divide as you do the ordinary division of polynomials. X square plus 1, when we divide the polynomial x4 plus 2x cube plus 3x square plus 3x plus 1 by it. So then first divide the highest order term, that is your x4 and x x square and x4. So first divide x4 by x square, you will get x uh, x square, then multiply this x square with 1, you will get, sorry, multiply this x square with this entire polynomial, you will get x4 plus x square. Subtract it, you will get 2x cube uh, plus, then this will be cancelled out. Uh, this will be cancelled out. You will get 2x cube plus 2x square plus 3x plus 1. Now again, it is the highest order term is x square, and here your highest order term to be 2x cube. So if you divide it, you will get 2x. Okay, then multiply this 2x with this entire polynomial x square plus x square plus 1, you will get 2x cube, 2x. Subtract them, this will be cancelled out, and you will have 2x square plus x plus 1. Again, look at the highest order term, x square, divide 2x square by x square, you will get 2. Multiply this 2 with the entire polynomial, you will get 2x square plus 2. If you must subtract it, it will become minus 2x square minus 2. So this will be cancelled out, and you are left with x minus 1. Now degree of x minus 1 is less than degree of x square plus 1. Its degree is 1 and its degree is 2. So you have to stop the division here. So your the quotient is x square plus 2x plus 2, and your remainder is x minus. Okay. Now we are at the last question of our mm, assignment. So it says, just a minute. We need to find the GCD of 1 minus 5i and 1 minus 3i in the ring of in the ring Zi of Gaussian integers. We can use Euclid's algorithm. So there are four options: minus 1 plus I, 2 plus I, 1 plus 2i, and I. Okay. So uh, I hope you know what is the norm of a Gaussian integer. Okay. So if you don't know that, then I can just write norm of a plus bi is just a square plus b square. Okay. So the norm here is the 1 minus norm of 1 minus 5i is uh, 1 plus minus 5 square, that is 1 plus 25. So its norm is 26, and norm of 1 minus 3i is 1 plus 9, that is 10. So uh, this element has a larger norm than this element. So we will apply Euclid's algorithm by dividing this element by this element. Okay. So we have one. So you can see that 1 minus 5i is 1 dot 1 minus 3i minus 2i. Just see, just try to divide this coefficient of I. So minus 5 is divisible by minus 3 by 1. So I have written here 1, and rest is considered as the remainder. Okay. So minus 2i I got as a remainder. Now the norm of minus 2i is 4. So yes, we will continue the division. 1 minus 3i is divisible by minus 2i. The percent is 1 and the remainder is 1 minus I. Okay, and 1 minus I is again non-zero. The norm of 1 minus I is 1 plus 1, which is equal to 2, which is equal to the GCD of the norms of these elements 10 and 26. So if they are uh, so this is a good candidate of the GCD of these elements. You can check it why. Okay. If it don't work, then we would have continued the process. But here we will try to see if we can explicitly divide, if 1 minus I explicitly divides 1 minus 5i or 1 minus 3i. Okay, so because 2 is the GCD of their individual norms, so any an element with the GCD having 2, it's a good candidate of of their GCD. If it don't work, then we will see if any associate of this element can do the job. If none of them is able to divide both 1 minus 5a and 1 minus 3a, then we would have used the Euclidean algorithm again, and then in the next step we would have checked whether the division happens or not. But here let's first check whether 1 minus I divides 1 minus 5i and 1 minus 3i. So if 1 minus I is uh, uh, let 1 minus I times y plus bi is 1 minus 3i, then you have a plus b plus minus a plus b times I is 1 minus 3i. So compare the coefficient of I and the constant term. You have a plus b to be 1 and minus a plus b to be minus 3. Thus you will get, after adding, you will get 2b equal to minus 2, which implies b is minus 1. And from here you will get a equal to 2. So it implies that 1 minus I divides 1 minus 3i. Okay. And if 1 minus I is c plus di times, if you take it and you equate it to 1 minus 5i, then you have c plus t plus minus c plus t. Just compare the coefficients. Here we have I also. To compare the coefficient, you will get c plus d to be 1 and minus c plus d to be minus 5. So solving for c and d, you will get 2d to be minus 4, that is d is minus 2. And putting it back to this equation, c plus d equal to 1, you will have c equal to 3. Thus 1 minus 5i divides 1 minus I divides 1 minus 5i. So all this helps you to conclude that 1 minus I, that GCD of 1 minus 3i and 1 minus 5i is 1 minus I. You can see that there is no option with by 1 minus I, but minus 1 plus I is also minus 1 plus I is just minus 1 times 1 minus I. Okay, so minus 1 plus I is also a GCD of 1 minus 3i and 1 minus 5i. So up to associate, the GCD may vary. So in Gaussian integers, mm, the GCD of 1 minus 5i and 1 minus 3i is minus 1 plus I. All other options are not correct. You can check why. See, what is the norm of this? Its norm is 4 plus 1, that is 5, which is bigger than the GCD of your individual norms. Here its norm is also 5, and I has norm 1, which is smaller than the GCD of these two. And we got a number which has norm equal to the GCD of the norm of 1 minus 3i and 1 minus 5i. So I I may divide these two, but I is not able to. But I has a smaller norm than this minus 1 plus I. So definitely it's not going to be the GCD. You can check whether I divides these two numbers or not. But even if it divides 1 minus 3i and 1 minus 5i, it's not going to be the GCD, because its norm is smaller than the norm of your uh, norm of minus 1 plus I. And minus 1 plus I is already dividing it. Okay, so that's it. Uh, uh, tomorrow, Shubhajit will take another help live interaction session in which he will discuss the rest of the seven problems from this assignment. And I request all of you to attend his lecture also, so that you get everything from this assignment. And if you have any doubt in any of these questions, you can uh, list out them, and we can discuss them in the next tutorial, next live interaction session. Uh, so yeah, that's it. We will meet again on next Friday at the same time from 6 to 7. And do attend Shubhajit lecture. He is also giving live interaction sessions on each Saturday. So do attend its session. We both are completing the same assignment. First eight questions I am dealing with, and the rest part is being dealt by Shubhajit. So if you want to understand the entire assignment, then it's good to attend both of us uh, live interaction sessions together. Okay, okay then. We will meet on next Friday from on 6 at 6 p.m. Okay.